Welcome to 8.1. This is our start of our unit where we really dig into quadratics. We saw a lot of quadratic functions in Chapter 7. We just never really referred to them as quadratic functions. And we didn't really look at graphs too much last unit, but that's going to be a lot of this unit is all the stuff breaking down the graphs of these guys. So a quadratic function is a nonlinear function. So again, we kind of stopped doing linear stuff after first semester. So exponential functions weren't linear, quadratic functions aren't linear, which means they change at a different rate, a different pattern. So it can be written in the standard form. Standard form, hopefully you remember from early on in chapter 7, that's highest exponent to lowest. Y equals ax squared plus bx plus c. The important thing there is it is a second degree function. Has a degree of 2. And a cannot be 0. If a is 0, well, then this first term doesn't really do anything. It doesn't exactly exist. So if a is 0, it's actually just a linear function. So we need to have an a value. B and C we can miss. We don't care if we have those. They make differences in our problems, but it doesn't need to have them to be considered a quadratic. This is the important term for it to be a quadratic. So then parabola is our other piece of vocab for now. Parabola is just the name for the U-shaped graph of a quadratic function. So parabolas are specifically used for quadratics. There's lots of graphs that might have a parabola shape, but parabolas are specific to quadratic functions. So here's a parabola. This is the basic quadratic. Sometimes we refer to this as the parent function. So it's just y equals x squared. In this situation, a is 1, b is 0, and c is 0. Since b and c are 0, we don't see the extra terms because it would be plus 0x plus 0. Well, those don't do anything. That's why we don't see them. But we could write it out as a full quadratic. So our goal with this graph is to start breaking down what are characteristics of a parabola. Well, we can always talk about domain and range. And just a reminder, domain is all of the possible x values. Range is all of the possible y values. So domain in this case, we have to ask ourselves, is there any number that can't be x? These lines look like they get really steep, but they actually go left and right forever. So if you think to yourself, squaring something just means multiplying it by itself. Is there any number I'm not allowed to multiply by itself? I can do 1.5 times 1.5, so I can do decimals. I can use negative numbers, like negative 3 times negative 3 would be positive 9. Obviously, I can use positive numbers. There are no illegal x values here, so domain is going to be all reals. Now range, that doesn't work for. If we look at the graph, there's this spot where it turns around. I'm going to use a red dashed line. So it's either going to be a floor or a ceiling of the graph. Wherever it turns around, it like not quite bounces off, but that's its turning point. This would be a minimum. So this is a floor in this problem, which means I do have a limit on my range. Range isn't going to be all reals. So this spot here is called the vertex. That is the vertex. So for us, the vertex is 0, 0, which means every point is going to be at or above 0. Range for this problem is going to be y greater than or equal to 0, because it can be 0 and it goes up from there, but it does not go anywhere below 0. So vertex you can think of as the middle or the turning point. So for our problem, vertex was 0, 0. And we have one more characteristic that we're really going to want to talk about, and that's the axis of symmetry. So we have a y-axis and we have an x-axis. Well, this is a new axis specific to the equation. It's the axis that the graph is symmetric around. So this is a vertical line where if I folded the graph over itself like a piece of paper, it would end up perfectly right on top of itself. So the axis of symmetry is always going to be an x value. In this case, it's x equals 0. Now, I'm going to use some more colors. The x value of the vertex will always match the axis of symmetry. So if we know one or the other, we can figure out the opposite one. So this is the middle line, not just the point, the whole line we could fold it over. So for our problem, it is x equals 0. So vertex is a point, axis of symmetry is a line. Point, line. All right, so those are all the characteristics we're really going to care about. There's other things too, like if I read my graph left to right, there are points where the graph is decreasing. It decreases over here, and it's going back up. It's increasing over here. So there's other stuff like that we can talk about. I mean, future lessons where we actually have B and C values, these things are going to matter more, and we're going to have a couple more characteristics. But for just the y equals x squared, this is going to be pretty typical. So there's a lot more to do in the coming lessons, but for now, just get used to the shape of this graph and where the parent function is. Let's look at how we might break down and graph some of these types of functions. So our basic parent graph, y equals x squared, is just the number times itself. -2 times -2 is +4. -1 times -1 is +1. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. All right, these parabolas are always going to be symmetric around a certain point. Today, it's always going to be 0. But in the future, that definitely won't be the case. It will always be symmetric around something. 0 only really happens when we don't have a b value. So y equals 2x squared. If I follow order of operations, I would do the exponent first. So I'm going to square it, and then I'm just going to multiply by 2 afterwards. So 0 times 0 is 0. 2 times 0 is still 0. -1 times -1 is 1. 1 times 2 is 2. -2 times -2 is +4. 2 times 4 is 8. So hopefully at this point you notice that I'm just going to end up doubling all of these times 2. This is called a vertical stretch or compression. This one is a stretch because it makes the numbers bigger at the x value, so it's going to be taller. A compression would be if this number was a fraction, and it would make my graph flatter and wider, so it looks like it's squished down, compressed. So I'm going to graph both of these. The y equals x squared is going to look like what we just had on the first page. Luckily, I have different colors, so I'll be able to show this off a little bit easier. So I'm definitely not going to be able to get as many points on for the second graph because it's going to get so much taller. So this is the graph of y equals x squared. And I'll use red. Let me write that a little lower so you can see it on the camera. I'll use red for the other function. I've got 0, 0 still, but now it's over 1 up 2, and then over 2 up 8. So it gets taller exactly twice as fast. So it still has that U shape, but now it's skinnier and taller at any given point. So the blue one was y equals x squared. The red one is y equals 2x squared. So So it's skinnier and taller, like you're stretching out a piece of gum or something. This is called a vertical stretch. So comparing these two, this one is exactly twice as tall. At any given point, it's twice as high up. All right, now there's other things that make it flop upside down, like if the a value is a negative number. Fractions will squish it flatter, but it's always going to have that U shape. It's always going to be a parabola.